Hi friends, welcome to our channel. In this video, we are going to look at problem 3563, lexicographically smallest string after adjacent removals. Uh, we are going to solve this problem using dynamic programming with the help of bitmask. So this problem is marked as hard. However, if you uh, decompose this problem into two smaller ingredients, then the overall logic will be straightforward. So basically, the operation here is the following. So we're going to do some removals of adjacent characters in the string that are consecutive in the alphabet, right? And also shift the remaining character to the left to fill the gap. And we consider the alphabet as circular. In other words, A and Z are consecutive. So actually, for the examples given, it's rather straightforward to interpret. For example, here, A, B, C. You can delete AB, and you can delete BC. But deleting BC gives A, which is lexicographically smallest, right? So this is what we want to output. So here, you can delete BC, and you can so you can first delete the CD in between, and then you have BA. BA are consecutive, so you can delete them. So you get empty one. So for the third example, the output is this because there's so we have D and C. But if you can delete the two characters, but you get a larger string in the sense of lexical order, right? So we just return the original one. So here the length of the S is bounded above by 255. This is also used to quantize the size of the problem, or in other words, control the time complexity. S consists only of lowercase English letters. This greatly simplifies the complexity of the problem, right? So with that said, we are ready to do the coding. So first, I want to make several parts so that you do not get lost. First, we can create a table to check if two characters are consecutive. So the table actually just gives the alphabet. So A maps to 0, B maps to 1, and then Z maps to 25. From 0 to 25, we have the overall 26 characters. So two characters, C1 and C2, are consecutive if and only if this condition holds. In other words, the corresponding values in the table, in the sense of modulo 26, differs by 1, right? This is one point. Another point when we construct the string is the item 2. So for two positions, let's say I is less than G, right? We can sit at I and look at the future positions to see if the corresponding characters can be matched and deleted. So the corresponding characters can be consecutive if the conditions in one holds. And this basically says that the two characters are adjacent consecutive in the alphabet. And if G is just G minus 1, I is 1, just next to each other, right? We can delete these two if we want. Or the middle substring can be removed recursively in the sense of the current problem. So this way makes the two characters at SI and SG matchable and deletable. It's like here, right? You can delete CD, and then the B and A, they match, right? Because those can be deleted. So this actually is a good demonstration. So then following the item 2, so how to check if I and G can be adjacent in the sense of the two corresponding characters. So in other words, if I can reach G, in other words, if we can make them adjacent and they actually consecutive. So for this, actually, we can build a bitmask list that's with length n, right? N is the length of the string, right? So if we look at position I, so we can look at the bits I. So this element encodes the information on which indices G, that is not those are larger than I, can be reached. For example, this can be checked this. If the G bit position is set, right? It means that we can make these two letters SI and SG matched. So the last question is how to construct the result, right? So with the preparation from the 1 up to item 3, so we can use DP, right? So we can initialize a DP. So here the DP table is length n minus 1. So n plus 1. So DPI would be the lexical smallest string obtainable from suffix from I inclusive and onwards. But here, if you look at this DP, the largest index is n, right? If the n is corresponding to an empty string, that's why we use empty string as an initialization. So then the DP up relation will be very straightforward. At index I, so we either leave SI unmatched with the larger indices, right? So then we just prefix this current character with the result corresponding to DPI plus 1. This is the one option. Another one is match it with some reachable key, right? So if SI and S key can be matched, so it means we can delete them. And then we continue from this DP key plus 1, right? But each time we need to save the lexical smaller result. So this will be the full strategy. So now what we want to do is to uh, um, mix this in code format. So here, if you look at the first line, so this is nothing but we get the ABC up to Z. So this ASCII lowercase is a string from A to Z. So this is used to build a table, right? So we can build a table using comprehension. So character IDX. So for IDX and character in enumerate ASCII lowercase. So once this is done, so we can actually build a list storing the corresponding index and position of the letters in this string S. So this can be easily done. So let me first have this S. So first we store the index and the positions. So here we can do this position. So for let's use a dummy index in 26, right? So this each index corresponding to this index here, right? And the list will store the indices of all the positions of the corresponding index a character in the position in S. So this is just a for loop. So for I character in enumerate S, then we know we first get the index, table character, right? This is the corresponding storing position, right? And then we are going to append, because it's a list, append I, right? So you can print out this for some visualization. For example, for this one, A appears in index 0, right? B appears in index 1, C appears in index 2, but other characters do not appear, so they corresponding to empty list. But this list, this out list has a length is 26, right? So we got this one. So now let's construct the reachable masks, right? So the mask corresponds to item 3. So for this, let's build bits as 0 times and n plus 1. Let's see. Let me just leave the last one to be 0, right? So what we can do is this. The reason we are using this n plus 1 because we want to use some increment 1 in between. So you'll see this. Let's bring some convenience. So for I in range, say n minus 1, -1, -1. So this is the beginning, this is the end. End is not included. And this is the increment. -1 is decreased by 1, right? So first we get the index in the table. So this is the table SI. Then we find the positions. So first we make a mask is 0. And then so the adjacent indices. So the adjacent indices will be this. So say this is the index +1 modulo 26 and minus 1 modulo 26. So you have, if you have negative 1, it corresponds, if c is 0, it's a, right? A 0 minus 1 is negative 1. Modulo 26, you are going to get 25. This corresponds to z. It means that it's a and z are consecutive. So we get this, right? So for d in this, this is the possible consecutive indices or consecutive characters in the sense of character. So we see the positions. So we are going to use this item 2. So for k in position d, right? So if k is less than or equal to I, this is the previous positions that we don't care. Then we look at the future conditions. So if k equals I plus 1, that's good. It means we can make them just connect to each other. And or, so the in between ones, we can make them removable. So this means this one can reach to position k minus 1. So let's use this. Then this one and 1. It means this is set, right? So if this is the case, so we're going to set this position at k. And also we inherit the reachable positions from k, so plus 1. So here you see k plus 1. If k is a minus 1, so k minus 1 will be 0, right? So that's why we have an index n. But if this n will always be 0, right? Nothing happens. This makes always work. You don't need to check if this key is a minus 1 or less, right? So this is the mask. So now we set bits of I to be the mask. So you can also print out this, right? Right. So you get this bits. So for this, basically, for example, at index 0, you have 1, 2. It means that 0 can match, can arrive at index 1. So because they have A, B. So here, 1, you can arrive at C, and because this C is 2, 4, the binary representation is 1, 0, 0. And so the second bit position from right is set. So you can also look at this one. So B, we can arrive at A, because, right? We can always also arrive here, right? Because 10 is like 8 plus 2. 8 will be 1, 0, 0, 0. 2 will be 1, 0. So bit position 2, bit position 1, and bit position 3 are set. So this is the bit position 1, this is bit position 3, right? So with that said, let's construct the result. So we're going to use suffix dynamic programming, right? So DP, so we're going to use this. So notice that this is immutable, right? So we can write like this. So, but this is always safe if you want to have something like this, or a dummy index in range m plus 1. But because here string is immutable thing, so we can write like this, right? So now what we want to do, so we iterate from backwards to the beginning. A minus 1, negative 1, negative 1, right? So in the current position, so the best result will be this. First, we consider this case. So we're going to use this one. So we leave this current character unmatched, then we prefix with dpi plus 1. So we have si plus dpi plus 1. At the very beginning, I is n minus 1, and I plus 1 will be n, right? So n, actually, this is empty, right? That's why we have this initialization. This also demonstrates that the initialization makes sense at the current interpretation of the DPR. So once we have this, then we also want to try this possibility, match some future indices. So let's first get the index, this table SI. Then we check uh, which we can match. So for D in, again, let's C plus 1 modulo 26 and C minus 1 modulo 26. So what we want to do is this. We will check the positions, okay, in position D. So if we want to check which indices we can match with this current I, right? So for again, actually roughly following this pattern. If k less than or equal to I, so we don't care about the previous ones, right? Continue. Previous indices. And then otherwise, if the indices have a larger than 1, or because at this condition, this in two characters at the position should be consecutive. Now, if their position is either adjacent originally or the in-between one can be removed. So it means that from I plus 1, right, and up to k minus 1, so it can be removed. So this means this one, this k minus 1 bit is set. Let's see, this should be a 1, right? If this is 1, and then the new candidate will be DP. So because we can match from character SI up to SQ, we can consider delete them. So this corresponds to DPQ plus 1, right? So then, as we said, we should always maintain the lexicographic smallest, smaller one. So if candidate is less than best in the sense of lexicographic order, so we set best to be candidate, right? So then afterwards, what should we do? We set DPI to be the best. So then actually we finish this loop. So what we want to return actually is return DP0, because DP0 means that the lexical string we can obtain from the whole original string S. This is the full code for the problem. Let me first run it. Yeah, it passes the 3 cases. Now let's look at the generic case. Yeah, it passes all the cases actually very fast. So with that said, I guess we finished the bulk of the work, the coding part. So now let me make some comments. The first comment is that in the current dynamic programming, so we use the bitmask to help us. This is one thing. Another thing is a detail. So when we initialize the bits, so we use it n plus 1, this n plus 1. But here what I wrote is, so here this one. But here you also the base is n plus 1. But you can use n, but you need to do some index check if they are inbound or outbound, right? So this is the detail. So the third comment is that actually we have a YouTube channel which has a big playlist on dynamic programming. I guess the dynamic programming is actually a very fundamental coding algorithm or coding technique you need to practice. And also we use bitmask. So bitmask can be very useful sometimes in brute force solution, and sometimes you can use less space, right? So we also have a playlist. You can use it to practice. So with that said, I guess that's it for the current video. Thank you for watching.